Ever heard someone say the more you do it, the more accurate it gets? That's not just a hunch, it's a statistical truth. Today, we explore the weak law of large numbers, the principle behind why your estimates get better as your data grows. Imagine flipping a coin. The probability of heads is 0.5, right? But if you flip it 10 times, you might get 7 heads, or 3. That doesn't seem like 50%. But what if you flip it 1,000 times, or 10,000? Suddenly, the proportion of heads starts to settle around 0.5. That's the power of the weak law of large numbers. It says your sample mean converges in probability to the true mean as your sample size grows. Formally, if you have a sequence of independent, identically distributed random variables, let's call them x1, x2, xn, each with a finite mean m, then xn1 1 nxi p m bar x n o m brots nanafrac 1 n gus sum y1 nan xi right x right arrow p mu xn n walana genda sip. That arrow means converges in probability. So as n, the probability that the sample mean is far from m becomes really small. Let's revisit the coin flip. Let's say shibyo 1 if toss-i is heads and 0 if e. It's tails. That's a Bernoulli Thi variable, where Thi is the probability of heads. The sample mean, xn bar x nxn, is just the proportion of heads. The WLLN tells us xn pth bar x n x right arrow p ertheta x n p's, so if Thi yan 0.5, then with enough flips, we'll see that 50% emerges heads. At least, very close to it. This law is the backbone of frequentist inference. It justifies why we can use our sample to estimate unknown population values. We don't need the exact value of the but we can trust that with enough data, our estimate gets arbitrarily close. From quality control to political polling, the weak law gives us confidence in using data to answer real-world questions. Next up, we'll talk about one of the most important tools in your statistical toolbox, the likelihood function, and how we use it to estimate unknown parameters, like eth. If you're finding this series helpful, don't forget to like and subscribe.